For this week's video, we're building an environmental sensor board. So we're looking for temperature, humidity and pressure. This is going to be an internal project, so it's not going to be weatherproof to go outside. So obviously you pick different components if you were doing that in a different housing. For this project, I'm using the TMP 117 from SparkFun, the SparkFun breakout board version of it. That's their high precision temperature sensor. And we also have the pressure sensor, which is the BMP 581, also from SparkFun. And for comparison and to gain humidity, I'm using a DHT22. This is a standard part, the DHT22, that you'd find in many common starter electronic project packs. It and its cheaper DHT12 are one of the first ones you play with. I've added it in this collection, one to gather humidity data and for a comparison to see how accurate it is against the pricier, more specific breakout boards. New to this project, moving from a DIY solution to a better solution, I'm using the Adafruit swirly backboard system. So this is their mounting board system for projects, particularly projects using breakout boards like this. It is a perforated aluminium circuit board that they have made to enable you to mount projects to it. So the boards have a screen print on the front with coordinates on them, so it's a two coordinate system like an array. So you have across and down. That makes it easier to plan where things are. It's a regular pattern with holes, so it's got a hole in the middle and then two wide holes on either side. But I also have a 5x5 block and a 10x10 block. Because it's made out of aluminium, it's electronically conductive. So to mount hardware components to it that are isolated from it, you have to use nylon nuts and bolts. They also sell that as part of the kit. I found the system very useful, particularly for this project, because it allowed me to mount all the different sensors separately but close enough together. So they're all isolated from each other, so they can't transfer heat from one to another. If I'm looking to obtain exact heat measurements, I don't want any bleed through from one sensor to another. So they're all mounted completely separately with air gaps between them. That way I can be assured that there's no heat travelling through the boards between them. As always, disclosure, all of this equipment was bought with my own money. I haven't been sponsored by any of the companies mentioned. So I will list all the prices as I've gone through so you can see how much I paid for each item. I was planning to use an Arduino R4 Wi-Fi board for the heart of this project, but unfortunately it didn't play nicely with my with the SparkFun breakout boards. This is likely due to the logic level being different. The Arduino runs at a 5-volt logic level. I assumed that the Quickie connector, or their version of it, would have a level shifter in it, but I don't believe it has. I think it outputs 3.3 volts as power, but I think it may still output 5 volts logic signals, so it didn't play nicely with those boards. So swapping it out for that, I have used the SparkFun Red Board Plus, and this has a toggle to switch between 5 volt or 3.3 volt system, so you can set the board to be one or the other at a hardware level. So I have set the board to 3.3 volts so that all the logic plays nicely together. Fortunately, the pressure sensor seems to be tolerant to 5 volts, so it didn't emit the magic blue smoke when I accidentally put the wrong voltage on it. But I wouldn't recommend doing that. So this is a nice and simple project, as with my last one, using their Quickie connector system. So it has a connector on the board. It's a 4-pin connector, so it has the data ground, then the power ground, and the 2 data pins, and that can daisy chain through the boards. So I'm going from the red board to the first sensor, and then daisy chain from that first sensor to the second sensor. For the DHT22, I'm going, it's a single pin operated board. So I've got power and ground, so I'm running 3.3 volts and ground to that board. And then the data pin to pin number 7 on the red board, so the Arduino clone. In reality, you're meant to use a resistor between the data pin and the ground to lower the input signal for the digital pin. I haven't done that in this case, and it seems to work fine without it, but it may vary from board to board, some boards might be more tolerant than others. So I'm leveraging 4 main libraries for this project, using wire.h for the wire communication, the SparkFun libraries for the TMP117 and the BMP581, so they are from SparkFun themselves, and the DHT library I'm using the Adafruit version of that. There are a number of versions of it, but I chose the Adafruit version. So then we have the different section. I've tried to keep the code clean. I've basically combined 3 different reading setups from the 3 different sensors using the libraries here, and then combined it into one bit of code. So we have defines the digital pin that is connected to, and then the type it is, because you have the DHT12, which is less good than the DHT22, but they're both in the same library because they're so commonly used interchangeably. And then we integrate the different sensors, so we have loading this sensor and then loading this sensor. The sensors have I2C addresses, so you can't have 2 sensors on the same address. So you see here the sensor TMP117 has a default address of 48, whereas the BMP581 has a default address of 47 with a backup address of 46. So you can't have 2 sensors with the same thing, otherwise they clash and they can't talk to each other correctly. There are workarounds with this, of course, but if you're looking for making a long chain of sensors or multiple sensors connected to one board, you have to keep that in mind. Then I have just a float for temperature, which I have sitting there. So the wire begins with a serial. I'm running serial at, 115,200, and then I have the clock speed set here. So I've got the different readings on 3 different sensors separated. So I've commented here and above where they start and end. So it tries to read the sensor. This is just to test to see if it can or not. It's a verification step. So I've got one for the TMP117 and for the second one, and the third one we haven't got a full setup. I'm just saying begin. So I'm just calling the function and hoping it works. In principle, you could add some more code here to verify it gets some data back, but I haven't bothered. Now moving on to the loop. So we have, I have tried to keep the sensors separately. This code is not optimized in any way. Of course, you can optimize it further. I'm just keeping it simple. So this is looking at the sensor to see if data is ready. If it is ready, it then reads the data and then saves it to a float. So this is for the TMP117. So this is our high precision temperature sensor. This records the data in a 16-bit resolution. So it's got a 0.0078 degree increment size between each reading. So it has very fine graduate readings. So it can be very small differences and it will pick it up. Obviously it's only reliable and accurate to 0.1 of a degree. But as you'll see in the data I've got in a minute, it's quite accurate and quite consistent. It doesn't jump about, there's not a lot of jitter. So what I've done here is by default the serial print system only prints 2 decimal places. So it gives me, say, 22.10, but it doesn't give me any decimal places after that. To achieve that within this, you just add another number here that denotes the number of decimal places. So in this case, I'm asking for 4 decimal places instead of the default 2. So that makes it so I can see the following 2 digits in my results down here. And then I've got delay here just because it was built in the initial code. You can probably remove that. Then we have our second sensor. So this is the barometer sensor. The measurement we're after here is the pressure, but we're getting this temperature as a secondary benefit. So it initiates the data, checks where the data is. If there is data, then it outputs the data to the serial terminal. Obviously you could save this data to a variable, which would probably be sensible, but as I'm just recording it off the terminal at the moment, I'm leaving it as is. And then of course there's a fail condition, so if it fails, then you'll get an error. Then for the DHT22 sensor, we're hunting for the humidity from this sensor for our project. So we're reading the humidity, saving it as float H, and then we're reading the temperature and saving it as T. So that's reading it, and then if it fails, then you get an error. You would have seen that in all of our code, we're recording everything in Celsius. This is the default option for all of the sensors. I looked behind the code and that's what it's been recorded as a primary recording method. It then converts it to Fahrenheit if you request Fahrenheit. So there's it built into the libraries as a conversion from Celsius to Fahrenheit. But it records Celsius and then converts it rather than the other way around. As I'm in the rest of the world, not in the US, I don't have an issue with that because I like Celsius. Then I have the data being output, so it's printing out the humidity with the H and T for the temperature, and then I just have a pause between readings before the whole loop starts again. So it's not a complicated set of code. You can improve the code and remove some of the delays to get more frequent readings, but as you see at the bottom here, we're getting readings, what's that, approximately every 1.1 seconds. So we're not talking a huge amount of time between readings. As this is a long-term temperature recording project, I don't think a recording speed faster than 1 a second is needed. We have the TMP 117 and the pressure sensor have a faster readout, so you can set it to output data in a lot faster rate, a lot faster hertz than the DHT22. I think that's got a slow read time between sensors. So that's why I've stuck it at the end of the list before the delay. So I left the device running for a couple of hours connected to my PC and used Putty as a data logging tool. It has a built-in data logging feature, so you can ask it to listen to the serial channel the Arduino is talking to, and then it will output a saved file with the data it received. I then changed it, I reformatted it via a few processes in Excel, and then created this chart. So at the bottom we have the number of samples, so it was about a sample every 1.1 seconds. So we have a little over 5,000 samples here, or nearly 5,500 samples here, and we're just looking at temperature here. TMP 117 sensor is in blue, the BHP 581 sensor is in orange, and the DHT sensor is in green. You can immediately see some differences between the sensors. So if I zoom in slightly, you can see that the DHT sensor isn't as granular as the other two. It only records in steps. So if the graph scale here is in 0.1 of a degree steps. So it would only record 22 or 22.1 degrees. It doesn't record anything in between. So you can see they're quite close together between all three of them. As you can see from the data, they can accurately pick temperatures one after another. There's not a huge amount of jitter or noise there, particularly the blue line, the high precision temperature sensor. It's quite accurate and quite consistent from one measurement to another. I was surprised to see how close they were in terms of accuracy between each other. So if we look at this point here, so the DHT22 is 22.1 degrees, whereas the barometer sensor is coming in at about 21.9. So we're about 0.2 of a degree difference between the two sensors, and obviously the blue line's in the middle. But in some areas where they're basically on top of each other, I think the widest gap is about 0.3 degrees between the whole range of it. So they're not far off from each other in terms of what temperature they're reporting. So any one of them would be an accurate representation within, say, half a degree of the real temperature, which is good considering how cheap the other things are. Another thing to note that the data shows is that the high precision temperature sensor doesn't suffer, or at least not in the dataset I have, from outlier values. So you have the other two sensors that suffer from high or low outlying values. These would be annoying to deal with in code. You'd need some sort of filtering in place. Otherwise the system would be panicked by the sudden drop of temperature of, say, half a degree, and then back up again half a degree the next point, or up half a degree and then back down again half a degree. They would trigger things that you wouldn't want to happen, because it would jump from one thing to another and then back to the real temperature. So you'd have to have some sort of filtering in place. Whereas the high precision temperature sensor didn't show any of that during my testing. Using all of the sensor data I received, you can see here, we can see the temperature. We got 3 different temperatures. Obviously we'll use the most accurate one as our main source of temperature, and then we can always use the other temperature sensors as a backup. So say if this one suddenly reports something that isn't expected, we can look at the other 2 temperature sensors and go, well, actually they're reporting it too, it must be something actually happening, rather than an error with one particular sensor. So you can do some sort of filtering that way. We have a pressure sensor, and that gives us the pressure in pascals. And then we have a humidity sensor. So we have the 3 different types of sensor that you use for an indoor sensor recording.